So our next session is going to be starting right now. It's going to be a case study given by Tushar Katarki, who worked on AI as a service platform on Openshift. Using AutoML and Kubernetes, they are able to run massive machine learning pipelines and improve the machine learning model automatically. Extremely interesting topic. Let's get started and welcome Tushar.
Thank you, Chung, and thanks everybody for coming here. Welcome. I'm super excited to be here, and I'm going to start my stop clock here so that I keep a track of time. I have a good amount of material to cover. Hope you're all having a good time here in San Diego in spite of the rain. The 1 or 2 days we are here, it decides to rain. So that's great. But this is going to be a much more interesting topic, so it's good that you are here. So let me introduce myself and my, let's start with Itay. Itay Gabbay is the machine learning lead for a team in the Ministry of Defense for Israel. And I and Itay have worked on this presentation. This is obviously based on the work that he and his team have done at the MOD. Unfortunately, he couldn't make it today, so I am going to be presenting this content on his behalf. Who am I? I am Tushar Katarki. I'm a product manager for Openshift at Red Hat. I have been there at Red Hat for several years now. And one of the things that I like about my job is that I get to talk to a lot of customers who are really using our product, Kubernetes. Openshift obviously is built upon that, and that's very exciting. I see a lot of different use cases, the problems that they run into, the escalations they bring. It's all a good challenge. So one of the favorite customers of ours and mine particularly is the Ministry of Defense. Obviously this is a large governmental organization, and what's happening there really is that, I'll use the clicker now, they are undergoing digital transformation, and a lot of companies are doing that. They're doing it with private cloud in mind, one of the major things that they want to do really there with the digital transformation is accelerate application delivery, accelerate R&D projects, and particularly of interest, obviously, for this talk is what they have done to do accelerate machine learning with this machine learning as a service, at the MOD. So if you take a step back and think about why so much of excitement in machine learning, the next 3 slides I kind of set up that a little bit, starting with what's it with the machine learning that we can do that you cannot do with traditional algorithms, and I do that with this illustration. Here on the left you can see that there is some data points, red and green, and classifying that using traditional methods is not easy, whereas with machine learning algorithms such as SVM in this particular case, it has transformed that data into a 3-dimensional space in which you can put this data plane which acts as the decision surface, and therefore you are now able to classify, right? So this is a simple example to illustrate the point. If you take it the next step forward, deep learning. Now, actually, I remember doing in grad school, undergraduate school, doing computer vision and object detection several years ago, 20 years ago. I'm dating myself. But the object detection since then, or that kind of traditional object detection, was more about, is this a yellow bus at the most? Right? Whereas, in the deep learning context, what you are trying to give it context. Like as humans, when you look at this picture on the left, you're not just thinking about the yellow bus, but you're also thinking about the road and the trees there and the grass, etc. On the right side, for example, it's a living room. You're thinking about, is it well organized? Is it eclectic, etc., etc. So humans actually think more complex, and that's something that deep learning can do. Deep learning can kind of think like humans. And an extreme example of that, obviously, and you know this, is when the Google DeepMind in the challenge match defeated the Go champion a few years ago, a couple of years ago. So this just is at least an illustration of how far we have come and what the possibilities are with AI, machine learning, and deep learning. So that's why this is exciting. This is not just a science project anymore. And therefore, so now let's look at what some of the characteristics of machine learning, what is so special about them, and that will build the story towards what then MOD had to do as a result, right? The first one really is, and I think we recognize this, most of us, is data. They are data and compute intensive. So how are they data intensive? The traditional methods here shown by the red arrow on the bottom, yeah, of course it needs some data, but then as you see there, as you throw more data, the accuracy doesn't increase any much. But if you look at the top graph there, or the top line, the large neural net, using deep learning, the accuracy of the model increases exponentially as the number of data you throw at it, right? So this is why these deep learning models are what are known as power hungry, right? Similarly, on the compute side, just going back from, this only charts from 2013 to 2018, look at the amount of computational capacity that these various machine learning algorithms and setups have done here. There's a 300,000 times increase, as you can see on this slide. So net, we know that they're data and compute intensive. What else? They're very iterative. This is a familiar model or a pipeline for workflow for most machine learning. You're familiar with it. There's preparation of data. There is feature extraction. There is you train models, you evaluate models. So why do you need to do it in an iterative fashion is because this is just as an illustration. This data here on the left side is just a tabular data, but it can be dirty, it can have duplicates, you need to kind of iteratively clean it, right, and filter it, and split the data into kind of what you need for model building and then for testing, right? So, and that is an iterative process. Similarly, when you build a model, we saw SVM, there are various ways, various algorithms, various models that can be applied at a problem. And then not only that, there are various optimizations that you want to do with it, hyperparameter tuning, and then you have cost constraints that you need to manage. And then this one just shows in a gradient descent, for example, there could be different lows, right? There could be local optimization points. So that's not the one you might want to be looking. So there's a lot of iteration, as you can see in this, a lot of different data is also used. Then finally, you have deployed your model into, you're satisfied, it meets your criteria, you have deployed it into production, but then also you can see here there can be drift, right? So this is an illustration of how that drift is happening. The data that is coming in, simple yellow data, initially has gradually changing over to blue data. So you've got to make sure that your model is able to account for it, right? So this is drift, and so you need to be able to monitor. So all in all, ML is iterative, right? The other thing that needs to happen is machine learning, most people think about as data science or data scientists doing machine learning modeling, but there's more than that to that, right? First of all, obviously, it is data scientists who want to collaborate with each other. They want to exchange models easily. Then there are other people involved in this, right? There could be data engineers who provide the data pipelines. There could be business analysts who decide or who at least have input as to what business problem you're trying to solve and what you're trying to optimize, et cetera. And then there are developers. Developers need to take all this and make them available as an application, as part of an overall application. So it is a very and then you want to be able to share it and just bring it into production, right? So this is a very collaborative and sharing model that characteristics that we have with this. So what was the journey with MOD? So the top 3 requirements based on the tee-up that I did, you can imagine this shouldn't come as a surprise. They wanted access to elastic compute. They needed that compute resources. They need access to, they want the ability for models to go into production. They want to optimize and scale this, right? So, and we'll talk about AutoML later in that context. So if you kind of put it in a nutshell, what does a data scientist want, right? Like a data scientist wants a cloud-like experience, where they have access to all the various modeling frameworks. You know that this is a very fast emerging field, and therefore new models and new modeling frameworks are coming out all the time. So they want the latest and greatest. They want access to data. They want access to compute, and this includes GPUs, etc., which was the case in the case of MOD. And then they want to be able to share and collaborate and then bring these things into production, or whatever production means in that particular organizational setting, so that they can actually deliver value, right? So there is a stat out there somewhere that a lot of these models don't go into production. So that's something that they didn't want not to do, right? So they wanted to put this into production. And so this is a conceptual model in some ways of what they wanted to get done, right? So this is really a self-service portal you'll see here in the middle, and then a data scientist or a set of data scientists can log in. They can use notebooks. They can do their experimentation. They can deploy it into production for inferencing, and they can bring it into application pipelines. So what they did this in steps, and every good solution, I personally believe, should be done in steps. So the first step was to create a self-service cloud-like experience. So this is, think about as the situation before they applied this solution, right? A bunch of data scientists, they have their individual machines. Some of them may even have GPUs, and they may have bulky machines. So they're not sharing this. They're siloed. They're not, the data that they access is bespoke. They can't share compute resources, etc. So to solve that, what do? They put that, all those nodes in a cluster, in a Kubernetes cluster, in an Openshift cluster, and they put Jupyter Hub. Jupyter Hub was basically their self-service portal for the data scientists, both for interactive as well as for just bad jobs kind of projects, right? So the data scientists were able to create their notebooks, do their experimentation, all that iterative work that I explained earlier, and so they were able to achieve this as the first step in the journey. So one of you saw it on the previous side, but one of the things that they wanted to achieve really is that they wanted some jobs or some kinds of projects required the access to multiple GPUs inside a container, whereas some others, they wanted to share GPUs. So they had both ends of the spectrum. So this is a way of me showing that a container is being shared, multiple GPUs are attached to a container so that the workload running in them can take advantage of these multiple GPUs. Whereas the next one is really about how you share a given GPU. GPU has a lot of CUDA cores and memory. So how do you share it among multiple containers, right? So they wrote something actually which was internal to make this happen. Obviously they have interest in kind of working with the community to upstream it. But then there is also a third method, which is really if your notebook is not interactive, you can basically run it as a Kubernetes job, and you'll see a little later how we do that correctly. But you basically establish a bunch of queues, and so jobs are coming in, and if the Kubernetes scheduler knows how to basically take up an entire GPU and assign it. And this works because all those machine learning algorithms, they're power hungry, right? Remember we talked about that. So they'll use it all 100% anyways, and so that should be okay. So the next step they did was multi-tenancy. Since there were a number of projects, a number of data scientists, they needed to do multi-tenancy. And again, we'll start with this OpenShift cluster with a bunch of nodes and the Jupyter Hub running on it. And then the next step you do is that you create, just as an illustration, you create a project called Echo, and using Kubernetes namespaces. Then you create a project called Tango, and then data scientists on this project are able to access data sets, and you create separate storage classes classes and PVCs, so that data scientists from this project Echo are able to only access data there and are able to do their modeling and experimentation, and data scientists from project Tango are able to access only data and resources on that side. And I won't go through each one of them because this is KubeCon, and you probably are already familiar with some of the ways to make this happen, using RBAC, using network policies, using storage classes per project or a namespace, and then resource isolation with everything from C groups all the way up to resource manager, and also having resource quotas. So you take that one step further. You want to be good neighbors with each other. Again, so the first thing you do is that GPUs are precious, so you don't want some arbitrary jobs which don't need GPUs to land on that. So you use taints and tolerations. You set up priority queues. Here, an illustration, I set up two, one with priority 1 and 99. You can actually have quotas for priority classes so that it is not abused. You can then start submitting Kubernetes, jobs or pods or what have you, with the toleration for these, and that would be kind of a hard way of doing it. Whereas if you want to use a more softer way to do that, you could use affinity and anti-affinity. And then now, obviously, if you do not want your data scientist to, write it in the pod spec, then you can create an admission controller, called for example, the GPU admission controller, which adds all these, to the pod before it lands to the scheduler. And then you can do other things, such as you can create multiple projects. We saw it on the previous page, and each project can have quotas for GPU usage. So there are ways to be good neighbors, and they as a journey, they did that with a POC, and then as they get into production, they implemented some of these features. So far what we have done really is that we have created, if you go back, they have created this self-service cloud-like experience for the data scientists, right? So the next step really was, what is known as AutoML, which I'll describe. But the problem that they were trying to solve really is that, we all know this, but data scientists are not, that talent is not easy to get, right? So what they really wanted to do is they wanted to be able to, obviously there are data scientists who know what they're doing, but then they wanted to kind of spread this talent, and for others who are not maybe who may not be subject matter experts to become these. So I think the premise really is, what if I told you that you can be an ML expert, right? So that's kind of the premise. And so what did they do? They introduced AutoML. So what is AutoML, right? So what you want is a model. You want some kind of a model or a set of models, right? And we all know that you start with data. And then you have something that you want to optimize, right? And then you have some set of constraints that you have for the problem. And then normally what you would have done really is that you would have done this, some data scientists would have picked the right machine learning model, and they would have done all the things that we talked about earlier. But what if we can automate it, right? So that we can, and that's basically what they did, right? So this is, the AutoML is a platform that basically automates the entire, for a given set of data and given set of optimization, given set of constraints, it tries different kinds of machine learning models and iterates it, and then produces something that is at the desired level of accuracy within the constraints that you have specified. So as an illustration, Itay actually just did a simulation. Obviously, he's not going to send real MOD data here, but as he gave me some, he did some illustration. So on the left, what as an ML expert, now you are the ML expert, what you can do is that you can go and access the self-service portal. They created this self-service portal, and then you can select a data set. Once you select the data set, the system imports it, and then it tries all these different models, it tunes it, and then when it reaches the desired level of accuracy, it actually selects that model and puts into production using a simple RESTful API, and that's what you see it on the right side. Here it simply says whether you actually have flu or not. I mean, it's a kind of a simple, and all this was running on top of OpenShift. Here you can see the scikit-learn pod running there, and then Jupyter Hub itself, and then, I mean, obviously we all know this. I mean, this is Kubernetes, so you can scale up and scale down, the number of pods. You can use HPA, or horizontal pod autoscaler, et cetera, et cetera. So we can have fun with this for sure. So what are some of the design elements that they chose? As I said, Jupyter Hub on which they built the portal. Then they used Ceph for storage. They used PostgreSQL for some metadata and as a catalog. And then they used RabbitMQ as the message queue. They used Flask to deploy those models as RESTful services. And all this was running on top of OpenShift. Sorry. So what are some of the results that they saw, right? So this is ultimately what we somehow care about, right? So they saw a 30% average improvement in machine learning model performance, a 70% increase in machine learning models, right? Again, this did not require that they scale the number of data scientists. This is because non-data scientists could take advantage of the AutoML platform, and they could create these services based on machine learning, and then explosive growth in the number of users using this platform. So that's all great. So what are some of the challenges and next steps that they are seeing? The first step really is, automate development. So one of the things is that right now this thing is great, but they wanted automation. They wanted to automate the end-to-end workflow, and I'll describe what that means in a later slide, because we are helping them with all of that. They wanted a better way to save. I mean, obviously all the models were saved, but a better way to catalog the experiments. They wanted to extend this AutoML to unstructured data like images and audio. They want to, again, have a better and supported way to do GPU sharing, and obviously multi-cluster. As this gets more and more popular, they want to be able to deploy more and more clusters, and so multi-cluster is really important for them. So what's next? And this really is the collaborative approach that we have from a Red Hat perspective, how we are working with them to realize some of these challenges. The first thing is, obviously, this is Red Hat, so we're always community first. So we're working with the communities, and I won't go into each one of these, obviously, but we are working with all the relevant machine learning and AI communities. Obviously, Kubeflow is obviously the big one there. And we are also working with some of the other ancillary in that context communities like Kafka and Mongo and Cassandra, all these other things that you need really to create an entire end-to-end system that we saw earlier. And we're working with, like, for example, NVIDIA and GC. So what we are doing is we have this operatorhub.io, and I'll describe what that is in the next page. But basically, this is a community-based website for where you can find operators for each one of these and more, right? And some of them might be in Kubeflow, for example, the PyTorch or the TensorFlow operator might be in Kubeflow. That's okay, but that's kind of where we are today. And then the other thing that we're doing is that we have this reference architecture called Open Data Hub. Again, this is upstream in the community, and that offers how to build a machine learning as a service, kind of similar what you saw earlier. On OpenShift. So this is basically how operatorhub.io looks like. You can see there are operators for all kinds of tools and software here. I won't go into each one of them. Open Data Hub itself, I'll describe next. So what it is the Open Data Hub really is that reference architecture. What it can do today is it can deploy all these components like Spark and Kafka for streaming for your data into OpenShift and into memory. Jupyter Hub is a self-service portal for data scientists for notebooks, both interactive and otherwise. There is Ceph for storage. There is Selden for inferencing. This comes from Kubeflow. And then there is Prometheus and Grafana to do to do the tracking, the monitoring that I mentioned earlier about drift, etc. And all this is deployed by Open Data Hub with this operator called the Open Data Hub operator, which then manages the end-to-end life cycle of all this. So that's one of the advantages that the Operator Hub has, or operators in general, an operator lifecycle manager has, is that they can manage the lifecycle if you want to update the Apache Spark due to whatever CVE, what have you, or there's a fix or a new feature, you can update it using the operator concept, right? So what else are we doing? OpenShift 4 itself, we're continuing to obviously invest, and we have a robust roadmap. GPU enabled, that's already there, nothing new there. But then we also have OpenShift Service Mesh with Istio and Agar and Prometheus and Kiali. Then we have Knative serverless with Knative and Tecton. And then all this can be basically deployed with the OpenShift installer on various infrastructure. So this is where they can scale, right? I bring it up only because I want to show that how they can scale as they want to do more clusters. One of the fundamental aspects is this. So how does this look like from experimentation to production with CI/CD? So this is the other thing. Remember, we said they wanted to do more automation. So how do you automate this end-to-end workflow for the data scientists? This is just an illustration. This is a data scientist with a notebook. They check it into a source repo such as Git. Then the source to image basically converts this notebook into a container image. It then gets deployed onto OpenShift, and then the iteration can happen. I mean, the notebook runs with whatever compute resources and data it needs, and then after there is enough accuracy of the model, and you're satisfied, it can then go into production, right? So you can promote and show the model in production. This is something that we already do for just vanilla applications, so why not do this for the data science pipeline, is what this is saying. And then you are continuously monitoring this for performance and drift, and you saw how the Open Data Hub actually deploys Prometheus and Grafana to make that happen. So that's the feedback loop, and that's how we create the iterative loop. So with that, I thought I would not actually reach the demo. I thought I would mumble along at some point, and I'd slow myself down. But luckily I have, so I will be able to show this demo to you guys. The demo is really, it's kind of rather simple, but it shows how Open Data Hub it can be used to deploy all those components that I just described onto OpenShift cluster. So it's rather simplistic, but I think it makes the point. So let's start with this. This is the OpenShift console. Some of you might be familiar with it. What you do is that you start by, I'll roll this and I'll pause it at some points, and then I'll explain what's going on. So the first thing really is that, as a admin, this is you are the admin and you are managing this cluster. You can create a project. In just a few seconds, if it is rolling, you'll see that as an admin, you're logged in. You will create a project, called the Open Data Hub project. You'll give it a name, the next step after that is that you will want to now install Open Data Hub via the Open Data Hub Operator Hub, and that's what you are going to see next. And you want to make Open Data Hub available in a select number of projects. You might want to do it for all the projects or namespaces in your cluster, but either ways, that's what you'll see here. You can browse down to this thing called the Embedded Operator Hub, and that basically has all the stuff that you saw on operatorhub.io, and then you can look for Open Data Hub operator, and then you can install it. You can see that that's happening here. It just says that it's a community operator. This is not something that is certified, or it's not a quote-unquote product. It has some more information here on what can be done with it. It shows all the things that it can deploy, the whole list, Grafana and Two Sigma and AI Library and Argo and Selden, et cetera, et cetera. But in this particular demo, we're just going to install Jupyter Hub and Spark for the purposes. Here is where that is happening, which I mentioned earlier. You can create an operator subscription, and you can do it to a specific namespace. In this case, the Open Data Hub, which you just created earlier. Following that, what's going to happen is that the Openshift, the controller is going to create this Openshift, the Open Data Hub operator. I'll speed this along a little bit because you can see that all those being created. Now you can see that the Open Data Hub operator has been installed. Now, as you go into it, now you can what I skipped over really is the fact that you logged out, and now you can be logging in as a user of that Open Data Hub project, and then you can create an instance of that Open Data Hub. And there you can modify the YAML, and here you can exactly choose what are the components that you want to deploy and what are the compute and memory that you want for each one of them. In this particular case, as I said, we are going to not deploy most of it except for Jupyter Hub and Spark. And so that's basically what's happening. We still have 5 minutes, so I'm going to let it roll, but we can have also some questions later. So let's see what's going on here. Okay, yeah. So this is just illustrating the fact that these are the various. I'll not speak for a minute so that you can absorb it. So monitoring is not being deployed. Like I said, I think the Spark and then you can modify the amount of CPU and memory that you want for that operator. And then I'll speed it along here a little bit. Obviously, it's editing YAML files is not that interesting, but you get the idea. And then you create it. Now the example Open Data Hub has been created. Now you can go to pods, and you can see that Jupyter Hub has been deployed, and then you can see that there is the Spark operator down below. So now it goes into how are you going to use it. So it'll go into routes in just a moment, and then a route is created to the Jupyter Hub, and so you are going to use that. You're going to click on that, and then you are able to log in into the Jupyter Hub. Just a second, you can sign it. So that's the other nice thing. You don't have to sign it again and again. You can sign it with Openshift credentials that you had previously logged in already. I believe that's what you can do. So let's keep going. And so this is what you get. This is the familiar spawner that you get with Jupyter Hub. Here, as you can see, you can pick from some pre-canned notebooks. This one happens to be a Spark, minimal Spark notebook operator. There you can see that you can pick different pre-canned container sizes. You can say this much, which have so much memory, CPU and memory. You can pick the number of GPUs you want for this, and then you can also add environmental variables such as AWS access key IDs, etc., for the data part of it. In this particular case, we don't use it because we are not using Ceph S3 in this particular demo, but that's something that you can do. So the next thing you do, you spawn the Spark operator, and this basically does a simple, and then in this particular case, you are going to get a simple notebook which is empty, and then this just shows you can upload your own notebooks and create a empty notebook, and it's just a simple hello world. Anyways, so that's kind of really what I wanted to show in terms of a simple demo on what happens, and I want to quickly go back to my presentation to conclude. to conclude, right, so in summary, what we saw today was the case study for MOD, how did they build a machine learning as a service platform using OpenShift and other open source technologies. We saw why they needed to build it and how they built a cloud-like experience. We saw how they built AutoML. We saw how Kubernetes and other OpenShift tools can help with this. And today, I mean, we don't have to wait for anything. And then finally, we saw what the Operator Hub and the Open Data Hub do. So with that, I'll conclude. These are my contact information, and we can open up for some Q&A. I'm be around, and so obviously, if we're kicked out, we can answer questions outside.